Is PowerPoint, are you able to see that?
Yes, sir.
Okay, thank you. So today I am going to discuss about the relativistic mass. Yesterday we discussed about the velocity addition rule has been uh, changed as per the what the Galilean sorry the Laurent transformations equation that we have, and similarly, I mean to say, if there is a that the classical laws is going to be a change in the special theory of relativity. Okay, the velocity addition rule is different because we need to take care of that postulate of the special theory of relativity. So, what will happen to the mass? Okay, if the body is moving with a certain mass, what is happening to that particular mass of that particular body? Okay, when it is in moving frame. Okay, so there is a certain phenomenon, okay, where the what mass is disintegrated and you need to change that mass is moving with a certain velocity. So the observer, which is in the another frame, or you say stationary frame, how it look at the moving mass, okay, and that the what the relativistic mass relation. So today we are going to derive that relativistic mass relation, relativistic relations with the help of uh, Einstein's relativistic theory. Okay, so yeah, so I'll continue the discussion on this part. So what do you mean by the Newtonian mechanics? So Newtonian mechanics talks about the absoluteness of a space and actually the mass which is going to be a constant every time. Okay, even though it's a body is moving with a certain velocity. But this is not the case with the relativistic case. Okay, here the like kinematic effect we learned the length and time that is going to be a change. Okay, here the velocity is also that's going to be a change. So here the mass which in a relativistic, okay, is going to be a change. So here we need to consider a certain again the same type of analogy where we have a one frame like one S frame over there and another frame that is a S prime frame over there, which is moving with a certain velocity v. Okay, here in with respect to that stationary frame, that is the S frame you have. Okay, and here we need to talking about the masses of the body. So we need to consider there is certain phenomenon where the what like two masses of the what, suppose we consider the two balls over here. Okay, which are in motion. Okay, and these motions of the bodies are towards each other. So these are the two balls we need to consider, and we need to consider their masses are m1 and m2 with respect to the S frame, and they are having the velocity u1 and u2. Means what the observer at the S frame, the constant frame, sees that okay, the moving mass has a mass m1 and m2, but look at their velocities are actually u1 and u2. But in the what the moving frame, that is what you have a S prime frame that has moved with a certain velocity. So we consider the mass of such a system, okay, m prime. Okay, so m prime represent the mass of the what the moving frame, and the u prime and the u, I say u1 prime or u prime, here it is mentioned small u prime. Okay, and minus u prime. Why the negative sign? Because these are the what the balls, two bodies which are in the approaching each other. So there the velocity, that is what the negative of the what the, because the observer sees that the velocity is what approaching. So I'll just say vectorially this one is the u prime, so another is the what the similar velocity with the negative sign minus u prime over there. Okay, so after the just like here to consider these two masses which are in motion, and after certain, I mean to say these two masses will collide with each other. Okay, and their resultant mass will be the simply what we generally the observer in S frame look at as a m1 plus m2. Okay, so here the two balls are actually moving towards each other, and their masses is now integrate. Okay, and the mass becomes a total m becomes a m1 plus m2. Okay, but what the resultant classically we write about the angular momentum relation. So angular momentum law says that the principle of conservation of the angular momentum, which talks about the resultant angular momentum should be a conserved. Okay, when this thing is happening. Okay, I mean to say when there is certain mass m1 is moving with, this is the mass m1 and m2 are those masses we are seeing from the stationary frame, and their velocities from the stationary frame are the u1 and u2. So when we are writing the linear momentum equation, you just product those mass and the velocities and add it together. So this is the m1 u1 is a linear momentum possessed by that mass m1, okay, has a velocity u1, and another mass m2 has a velocity u2. So their resultant momentum, conservation of momentum, m1 plus u1 plus m2 by u2, and that should be when they are collide with each other, and their resultant masses, I say m1 plus m2, that's the mass addition by seized by the observer which is at the rest. Okay, but that becomes a v because the observer is not locating at the masses, I mean to say the moving frame. We know that that moving frame is moving with this velocity. Okay, so m1 plus m2 are the resultant mass and multiply by the v, that gives me the resultant momentum. Okay, so law of conservation of linear momentum here, I say m1 u1 plus m2 u2 is equal to m1 plus m2 times v. Okay, hope you understand why we are writing this particularly law of conservation of momentum. Okay, so this is the equation which can be write about by taking, okay, the two masses m1 m2 has the velocities u1 and u2 in the race frame. If they combine together, and that's their masses will be added, but with the that mass with the product of the what with which that complete system is moving. Okay, and that's the velocity v. So hope you get the mathematical stuff over here, m1 which is m1 v over here and m1 u1. So when we I common it out, so the m1 u1 minus v, so this will be coming on that side, and also m2 when I take the m2 common over here, so this will be coming on this side, so v minus u2. Okay, so hope you know about this mathematical form, and we got this relation m1 m2 as equal to v minus u2 and I'll say u1 minus v divided by u1 minus v. So we got this ratio of m1 to m2 as v minus u2, okay, divided by u1 minus v. Okay, now the Laurent velocity transformation. This is the equation we yesterday we talked about. Okay, the relativistic addition law says that, okay, it's not simply the velocity you are writing about one mass or one component, particular mass. Okay, simply as a u dash or u prime plus v. Okay, no, it should be divided by this factor 1 plus v by c square into u prime. So here the Laurent transformation of velocity addition law, that's the law we use it over here for writing the resultant velocity of the u1 in terms of what the uh, the the velocity of the what the whole I mean to say when they are together, they comes together, their result velocity the u prime over there. So I'm writing the here the velocity of this u1 in terms of the what the when they are collide together. Okay, their velocities. Okay, u so u1 I just express in terms of the what the u prime, so that is in the positive direction. That's what over here the u prime, and the velocity with which that frame is moving is plus v divided by 1 plus v by c square by u. Now the second case, remember here how we are writing the velocity of u2. Look at this is the velocity of u2 you are writing. Okay, the what the observer here seeing these two phenomenon. Okay, so u1 u2 are the what the velocities of these one particle. Okay, in terms of the what this resultant velocity u prime that you are finding, but these are the u1 u2 are the already discussed about. These are the velocities of their masses m1 m2 in the what that constant frame, that is the stationary frame you have. Hope you got it. And now this u2 you need to express as minus sign over here. Why? Because that's the particle which is going on the what the I mean to say approaching directions. Okay, so this mass will feel that that mass is coming to, or this mass will see that that mass is coming to. So their resultant velocities are the opposite direction. So what? There will be a sign of minus u prime. Okay, and as it is, you need to add plus v, but 1 plus of v by c square. But this quantity now going to be a change as a u prime as a minus sign over there, and that's why there is a negative sign over here. So hope you know about this equation, this y minus signs I am talking. Okay, there's another mass m2 which is approaching toward the previous mass, or you say. Okay, so you need to consider when the first one is in the positive sense. Okay, the another one is the value having the what, the negative direction. Okay, so that the magnitude of that velocity we need to talk about is u1 and u2. Okay, now here the mathematical things. Why? Because you already written over here the m1 by m2 as a v minus u2 and u1 minus v. So you need to calculate this u2 by this formula, and you know that how the u1 you can write it. Okay, with this formula. So you know these two formulas, and now you can just express these equations and solve the ratio of m1 and m2. Okay, so hope you understand this part now. Why this part been written m1 and m2? I need to have to check these values. I'll just put those values. Okay, so v minus u2, and this is the value of u2 that been putted, and the another one is a u1 minus v. Okay, so u1 value is putted over here. So this is the mathematical thing. So how can you expand the things and just taking the certain things common? I think you can solve this mathematics very well. No problem on solving this particular part. Okay. And by the way, if you're not understand what exactly been doing over here, this is just like a this product. Okay, here, so it is a product when the two things are divided, so you just make a product. Okay, and solve this case. Okay, so that way it is done. I mean to say multiplying with this factor over here and just expanding and putting that equation in the numerator to denominator to have the what that sign. I mean to say that the denominator becomes a numerator when you have a product sign over here. I think there is no problem on mathematics part, but just the rearrangements of the terms you need to do over here and take the certain things common and express in a certain way that okay, you will get this common thing. I mean to say u prime minus v by c square u prime over there, and 1 plus v by c square u prime over there. Similarly, v minus v by c square u prime and u prime minus v by c square u prime. So you need to solve that to get this particular terms, and you will find that these terms on the numerator and denominators are getting cancelled. You try to do it yourself. You will get these relations. Yeah, in the blackboard I can easily do, but it you can do it. Okay, no problem. You just do this arrangement and check the ultimate equation what we need. We got this m1 and m2 as a ratio of 1 by v square u prime and 1 minus v by c square u prime. Okay, that is the ratio of m1 and m2 you are getting. Yeah, there are certain way of doing the things. This is the one of the way of solving to get. Okay, there are other ways also you can solve it. Ultimately, we need to find out the relation. Okay, how these masses m1 m2 are expressed in terms of the velocities. Okay, so how this u1 square comes. Okay, this the u1 square which come from that relativistic addition law. So you have u1 over here. Okay, so u1 you want to have to square it. Okay, sorry. So if you want to have square the u1 value, just 1 minute. Yeah, so u1 square means just square these things and square the whole term over here. Okay, when you do this square, so u prime plus v whole square and that division of 1 plus v by c square u prime over there. So you can do that things, and if you expanded that, so u1 square is equal to u prime square plus twice u prime v. This is the product rule plus v square. I mean to say a plus b whole square. That is a a square plus twice ab plus b square. So that's the quadratic equation, you got it. And similarly you solved the bottom equations, okay, with a certain arrangement over here. Okay, so we need to not worry about right now the how the expressions been solved. Okay, this is not to be asked in the examination, since we have always online examination, but you people have to practice those derivations, how those calculations to be need to be done. Okay, so here u1 square by c square been calculated, and then we need to have this form 1 minus u1 square by c square. So whole thing, that particular thing is subtracted from the 1. Okay, so 1 minus that whole things and solved further equations. Okay, to have all the arrangement again. Okay, so the things are that 1 minus, so 1 minus and whole thing, so 1 with the product with these things minus these things divided by this particular factor. Again the mathematical terms to be involved and solved to have the thing certain common over here. So once you got this relation 1 minus v square by c square means c to the power 4 u prime square. So there is a one common factor which is coming at 1 minus v square by c square. That is what 1 minus v square by c square, that is into 1 minus, if you common it out, u prime square by c square, then again there is a 1 minus v square by c square which is remaining. Okay, so here this term 1 minus v square by c square minus, if you common it out, there is a 1 minus v square by c square. Okay, so this is the arrangement you have to be careful and need to do, because I need to have those equations. Why we need to have those equations? Because here if you see that the m1 by m2's ratio will be a like that. Okay, and that particular m1 and m2, here we need to express in a such a way that, I mean to say, this is the quantity which 1 plus v by c square u prime and 1 minus v square by c square u prime, that we need to find it by certain arrangement, and that's what we are doing over here. U1 square and then 1 minus u square by c square, like that, to have a certain final value. Okay, so 1 minus u square by c square and u1 u2 square by c square and 1 minus u1 square by c square. Okay, if you do their ratios, their values you can just express here as in the form of this particular equations. I mean to say, m1 and m2 you are getting as a ratio of that 1 by v square by c square u prime. Already I mentioned here 1 plus v by c square u prime and 1 minus v by c square u prime. That's what the ratio of m1 and m2. And further, if you solve by this way, you got it, this 1 by v square v by c square u prime whole square, 1 minus v by c square u prime whole square, this quantity which is coming out as a ratio of these two. Okay, 1 minus u2 square by c square to the ratio of 1 minus u1 square by c square. So can we express? Yes, we can express this quantity. Okay, we know that this is the quantity of m1 and m2. So square root of this quantity will be a nothing but a m1 and m2, and that's what the square root over here, 1 by 2 power 1 minus u2 square by c square to the power 1 by 2, and similarly on the denominator 1 minus u1 square by c square to the power 1 by 2. Okay, so that the quantity you are getting square root, you say, okay, power 1 by 2, that's the ratio of m1 by m2 over there. So again, if I solve this, I mean to say 1 minus, so cross product we are doing m1 with the 1 minus u1 square by c square to the power half, and this cross product, you can write it, this is the term like m1 into 1 minus u1 square by c square to the power half. Okay, that is equal to m2 1 minus u2 square c to the power half. Like there is a what, these are the all m1 and m2 which are the initially are the constant, and the u1 u2 are the velocities we are talking about, those velocities, which is what, the velocities of those two masses, okay, u1 a2 at with respect to the stationary frame, and that is always a constant, u1 u2. So this quantity is coming to be a constant. We call this quantity as a rest mass m0. Okay, So here, if you are writing general equation m1 m2 m1 into 1 minus u1 square by c square, m2 into 1 minus u2 to square, where if there is certain other mass like m3 into 1 minus u3 square by c square to the power half, like that you can write down this as a similar quantity, okay, which is coming as a constant, and that is what the rest mass of the identical ball you have, okay. So if a mass is moving with a certain velocity v relative to the observer, okay, so how can we express this quantity which is coming m1, m2, m3, and so on? That has a mass m over there. That has a mass a constant m0 over there. That what we say that the mass resultant mass that the observer sees over there, and this particular quantity I may express over here, okay. So in general u1 u2 u3 or so on, that has expressed as what v over there. So m into square root of 1 minus v square by c square, can we write it as a some constant m0? Yes, we can write down. In general, this product, okay, m into, just like the product of here m1 into 1 minus u1 square by c square, another product m2 into 1 minus u2 square by c square. So in general, if the whole that whole particular thing is moving with a certain velocity v, okay, so that m1 m2 and m, that has supposed to be replaced with the common mass m, and all those velocities are to be replaced with a certain velocity v over there, okay. That I say this is the mass which is moving with the certain velocity v. Here the m1 mass is moving with the u1 velocity, m2 mass is moving with another u2 velocity. Suppose there is another mass m3 which is moving with the m3 u3 velocity. So in general, we can express this as a right hand side as a constant, which talks about the rest mass of the that particular balls that we are considered over here. And we got a relation, of the relativistic mass, okay. Relativistic mass is that mass which is moving with a certain velocity v, comparable to the speed of light, okay. So the resultant mass, I mean to say the object mass or a certain mass, what we consider over here the rest mass m0, that is going to be a change, over here. M is not equals to m0, so relativistic mass is your moving mass, small m, okay. And m, which is m0, you talk about the constant mass or the mass which is at the rest, that has to be a, I mean to say that moving mass is going to be a change typically on this particular factor, square root of 1 minus v square by c square. So here, when the object starts to move with a certain velocity with respect to the observer, how can you just appears that particular mass? So here the appears mass, this is like you have an equation for the time dilations, okay, where the what the whole factor is divided, okay. So the moving mass which is appear to be increase, okay, and that whatever be the by m0 value is looks to be increased, and m you have to be expressed in terms of whatever be the value of m0, that moving mass m is definitely more than that of the m0 because of this factor square root of 1 minus v square by c square, which is coming on the denominator side. So relativistic mass, I say m, that is a moving mass that is approaching, you say, when it is velocity 0, I say velocity 0, so this will be a 0, m becomes m0, okay. And when the velocity is c over there, okay, I mean to say v becomes a velocity of light, so c square, so 1 minus 1 is 0, that's infinite, so m becomes infinite over there, so it is more, so something upon 0 is infinite, so m is going to be increased when you have what velocity is going to be increased. So hope you understand this relativistic mass relation that what we derived today. And what I want to in general conclude over here is that the rest mass, that what the classical mass that the observer generally sees, okay, is not the same when the relativistic mass, that the moving mass, is a differ, and it is a totally depending upon the moving, I mean to say what velocity, that particular mass is moving. Okay, so that the name, that's the what we called it as a relativistic mass. Hope you understand how we got to know this relativistic mass relation. So all this arrangement and all those expressions we did it to understand the classical things is discarded over here. Okay, the ultimate thing is what the moving mass is typically depending upon the velocity with which it is moving, and we also know the relations of what those relativistic addition rule and all those formulas. Yes.
Sir, will you go to the last formula, final formula that you got? Yeah.
This one.
ह्याच्यावरनं असं म्हणू शकतो की म्हणजे मास जे रिलेटिव्हिस्टिक मास आहे हे फ्रेम वेलॉसिटीवर डिपेंड नाहीये, तर जे ऑब्जेक्ट मूव्ह होते त्याच्या वेलॉसिटीवर डिपेंड आहे.
करेक्ट. पण म्हणजे आता तू इथे जनरलाइज केलंय, म्हणजे तू काय केलंय की सगळे मासेस काहीतरी होत असतील, त्यांचे ते मासेस म्हणजे ऑल दोज मासेस अँड द प्रॉडक्ट विथ द स्क्वेअर रूट ऑफ velocity by c square, square root. Okay, that factor, yes, that depends upon the velocity with which that particular mass is moving in that reference. Yes, correct.
फॉर
बरोबर.
म्हणजे एखादी फ्रेम ऑफ रेफरन्स आहे आणि त्याच्यात बॉल काहीतरी स्पीड मध्ये मूव्ह होत आहे आणि त्याच्या दुसऱ्या फ्रेम मधनं जर बघितलं आणि तर मला असं दिसेल की त्या बॉलचा मास वाढलाय.
बरोबर.
आणि ते डिपेंड, ते मास कशावर डिपेंड राहील तर रेस्ट फ्रेम मध्ये त्या बॉलची स्पीड किती होते ह्याच्यावर.
करेक्ट. तर म्हणजे सपोज
म्हणजे मी माझ्या या ऑब्झर्वेबल फ्रेम ऑफ रेफरन्सची स्पीड डझंट मॅटर हिअर.
हा बरोबर. कारण आपण आता इथे काय केलंय, कारण इथे काय केलंय आपण, ही जी वेलॉसिटी अल्टिमेटली v इथे लिहिलेली आहे, पण डोंट कन्फ्यूज. म्हणजे प्रत्येक वेळेस आपण म्हणतो की मुव्हिंग फ्रेम आहे, मुव्हिंग विथ सर्टन वेलॉसिटी, इथे म्हणतो ना जे मुव्हिंग फ्रेम आहे, बट अल्टिमेटली त्या मासची जी वेलॉसिटी आहे, ओके what that particular mass is moving respect to the observer, that matters over here. Yes, correct. ओके, सो मास झालं तर मग आपण एनर्जी कडे जाऊ शकतो, कारण वेलॉसिटी झालं, मास झालं, सो एनर्जी रिलेशन्स वी कॅन डिराइव्ह. सो हिअर आय कॅन कम टू दिस रिलेशन नाउ. The classically, I mean to say the mc square, that the relations of energy mass relation, Einstein's famous mass relations that we know, and that we need to check over here in the relativistically. How's that rest mass of the body? I mean to say, suppose there is a particle which has a rest mass m0, so how much energy associated with that particle? That's elementary particle energy, is a rest mass energy that particle has. And if it is moving with a certain velocity, so force act, so there is a distance. Suppose this is the what we have to consider the kinetic energy. So classically, we know those Newtonian equations over here. The energy you can express with the second law of motion. Okay, the force is equal to mass. I mean to say the force into displacement, that the energy you can express. So generally you say that this is the kinetic energy which is increases. So don't confuse over here the total energy. I'm just talking about the rest mass energy is whatever be the mass that particle possesses, you just multiply with the square of speed of light, that the energy E suffix 0, we call that as rest mass energy. But here E suffix K is the energy when the particle has gained certain, I mean to say displace, it has energy, and that energy is a kinetic energy. So that kinetic energy gained by a certain particle we express in terms of the work done by that particle or work done on that particle. So force into displacement is a Newton's second law, says that whatever be the force multiply magnitude of force and displacement, that tells me that gives me the work over there. And that's the what the work done is. Suppose I'll writing for the small displacement dx is a dek over here, the whatever be the energy change, amount of energy or the work done. So dek represent the work done over here. So magnitude of force that you want to express with the help of the second, here the again what we are going to explain. So So again, second Newton's second law, P is equal to, I mean to say, linear momentum you express as a mv, but force you have to express as what, the rate at which this momentum is going to be a change. So that is your force. So this is the classical expression. Hope you know that this. Okay. So the d by dt, the time changing with the momentum, is your the force over here. Okay. So d by dt into mv gives me a force, and that value you can express over here, F is equal to d by dt mv. So that particular force you have to put it in this expression. So your expression for the energy becomes dek is equal to d by dt mv into dx. Okay. So this is a total differentiation upon, suppose, write dmv over here and rearrange the term as a dx by dt. So dx by dt gives me the velocity, and this is the differentiation, total differentiation of mass into velocity. So v is outside, with small d is represent the differentiation. Okay, don't express it as the distance or like that. Okay, it's a differentiation. So d over here, the differentiation, total differentiation, and that differentiation of what, the two product quantities, which is a one is a mass and another is a v velocity. Okay, here. So we know that particle start its motion from the rest, so initial velocity is zero, but at a certain time it acquires certain velocity v under the action of that force. So we call that final velocity is a v over there, and initial velocity is zero. So if you want to find out the total amount of energy gained by that particle, in doing so, how to do that? You just integrate this dek over the limit 0 to v and just do the integration. So you know that the relation here, the integration is there, and the differentiation, which are the what, the inverse effect over there. So they are going to be a cancelled. Okay. So you can simply here, I'm sorry here. So ek is equal to 0 to v, these things. Why I want to express this m is equal to m0? This is the, just ultimately we found out that the variation of mass is not the rest mass, it is totally depending upon the velocity with which that mass is moving. So it's m, we need to express as m0 divided by square root of 1 minus v square by c square. So this factor 1 minus v square by c square to the power minus half, which is written as a gamma factor over here. Okay. So gamma factor, we just write it as 1 minus v square to the power minus half. So m can be expressed as gamma times m0. Okay. For just for understanding, for doing what is actually the gamma. So gamma is just for understanding, it's a 1 minus v square by c square, sorry, v square by c square to the power minus half. So that we need to differentiate, because that also involves the velocity, and we need to differentiate this gamma with respect to the velocity. That means differentiation with respect to v. Okay. So when you are doing the differentiation with respect to v, and you have to solve this total differentiation, so it will be a what? 1 minus v square by c square, but it's a minus half over there. So it's a minus half times, okay, 1 minus v square by c square into what? Twice v by c square. Hope you know that. So that minus half and plus half, that with the what? A minus half minus 1, that the relation, you know that. I just use it over here, the derivation of differentiation, or you say differentiation of this particular term. Okay. Or you say some term which has a power minus half. So when you are taking differentiation of 1 minus v square by c square to the power minus half, the answer could comes out to be a minus half into, okay, this whole term, 1 minus v square by c square. Okay, 1 minus v square by c square, and then you need to I mean to say the factor, that minus half minus 1. Okay, minus half minus 1 over here, and the differentiation of this term over there, which comes out to be a minus of twice v by c square. Okay, hope you understand this differentiation over here, how this term comes. Okay, so this term which gives me an answer, this twice is twice get cancelled, minus half and minus 1 becomes a minus 3 by 2. And that's what you will get, d gamma is equal to v by c square 1 minus v square by c square to the power minus 3 by 2 into a d gamma. Okay, so that's the gamma factor we are writing over here. And now you have the ultimate energy that you need to calculate, the kinetic energy, which is the integration of this dek that you express as derivation of mv over there, and m you express as a what, m0 upon square root of 1 minus v square by c square. And you have to solve, and you just express that as a gamma factor over there, that is a gamma m0. You just write m as a gamma m0, but gamma is 1 minus v square by c square to the power minus half, remember. So this quantity ek, which comes out to be m0, which is the constant rest mass which comes out of the integration sign, and the variation from the 0 to v of vd gamma times v over there. Okay, and d is a what, derivation. So product rule you are using over here. The first function into the differentiation of second plus second into the differentiation of first, like that. So this product rule of the derivation, we are going to use it over here, and we write that expansions over here. Okay, and if you do that, and if you can find it out that, and by putting those values of the gamma, I mean to say gamma is ultimately 1 minus v square by c square to the power minus half, solve it further, this factor is coming common out, you will express now the d gamma v, okay, which I mean to say ultimately you have the d gamma v, which comes out to be a dv upon 1 minus v square by c square to the power 3 by 2. Or you say in the numerator, if you are writing here in the denominator, that's what its power is plus 3 by 2. So equations, these are the equations you can ultimately getting, and no problem, they're all mathematics part. But d gamma v, that comes out to be this factor, and you need to express now your energy, which comes out to be ek, and that quantity you need to just sorry, so here we need to just do that thing, and to find out the d by dv. So look at d by dv of 1 minus v square by c square to the power minus half. If you solve further, this equation we already got it. Okay, we need to rearrange this term in a such a way that there is a c square which is a constant. If it is a multiply by d by dv 1 minus v square by 2, so you can write down this as a simply v times 1 minus v square by c square to the power minus 3 by 2. This is the quantity you need to write it over here, just to I mean to say, to have a common to have to solution to simplify further. Okay, that's the things over here. So here the quantity which is comes out to be a m naught c square, and then the integration of this 0 to d by dv, 0 to v d by dv of 1 minus v square by c square. Okay, now ultimately here the integration is there of the limit 0 to v, the differentiation is there with respect to the v. So like these are like inverse relations. Again here comebacks, so they are I mean to say they just cancelled out that effect, and 1 minus v square by c square to the minus half can be written as 1 over square root of 1 minus v square by c square with the limit 0 to v. You just put those values of upper limit and lower limit, higher limit minus the lower limit, you can solve and get this relation, which is kinetic energy. Look at this, is the energy gained by that particle expressed in terms of the rest mass energy, that is m naught c square, multiply by this factor. Remember that 1 minus square root of 1 minus by c square minus 1 over there. If you expand it further, your ek will be a what, this value, I mean to say m naught c square divided by square root of 1 minus v square by c square, which again you have a relativistic mass, that is m naught divided by square root of 1 minus v square by c square, which is a moving mass m, and that the moving mass m has a certain energy c square, that gives me the total energy. So mc square is a total energy of the particle, while the ek is the kinetic energy that particle. So this relation which gives me the answer as what? The kinetic energy as the difference of the total energy with the rest mass energy. So kinetic energy can be expressed as the total energy minus the rest mass energy. That the ultimate relations you are getting over here. So total energy of the particle, you say that kinetic energy plus rest mass energy, okay, or you say the kinetic energy of the particle that you express of that particular particle. Just you need to write that total energy expression, which is mc square, but that total energy is expressed as over here m naught upon square root of 1 minus c square. If the moving mass has a certain rest mass m0, then we write m naught c square upon square root of 1 minus v square by c square. This whole quantity is a total energy of the particle, and m naught c square is like elementary particle. If you consider, it always has the rest mass energy m naught c square. So here we are getting the relation, that is the relativistic kinetic energy relation expressed in terms of moving mass or the increase in its mass. We always say that mass of the particle is increases when it has a certain velocity comparable to the speed, but that's the moving mass seized by that the observer, which is at the rest frame. So so kinetic energy and the rest mass energy gives me the total energy E. So whenever this function E is coming, okay, you called it as the total energy. When there is a E suffix K, it's a kinetic energy, and you added the rest mass energy with the suffix E suffix with the E0. So when you're writing this equation for the kinetic energy, you always write m minus m naught. Okay, so that's the m is the what, the moving mass, and that minus m naught is the rest mass. So m minus m naught c square by mc square. So your equation E is equal to mc square you are getting. So ultimately you have to express the kinetic energy in terms of the rest mass energy m naught c square. Okay, so this m naught c square is a rest mass energy divided by square root of 1 minus v square by c square. So the relativistic energy, total energy of the particle, okay, is always expressed by this way. So this is Einstein's mass energy relation, which comes to be a change when we are say okay, that particular mass is moving with a certain velocity v over there. Okay, so Einstein's relation, that mass energy relation, you ultimately have mc square, but that m here we are talking about the moving mass. Okay, relativistic mass. That relativistic mass is always expressed in terms of rest mass. So you always express as m naught upon square root of 1 minus v square by c square. So hope you understand this derivation, and there are certain cases we can solve further to see what the case if you have the velocity is very less than the speed of light. When the velocity is very less than speed of light, okay, then we can approximate the things. Okay, and the approximations, if you're writing and neglecting the higher order, okay, we can express as simply that kinetic energy. So when the v is very less than c, so when the velocity of that particle is very less comparable to the speed of light, your energy equation, that kinetic energy equation, classically leads to the half of mv square equation. Okay, so your mass is the rest mass m naught, and that's the velocity represented by with which it is that thing is moving. So half of m naught into v square, that the classical relation you have. Okay, however, the relativistic relation that you always remember, okay, that you derived over here is is this quantity. Okay, m naught c square divided by square root of 1 minus v square by minus 1, which comes out to the mc square minus m naught c square. Okay, so this half of mv square, that relation you get it from here. Okay, that's what you say ultimate approximation when the v is very less than the c. Okay, and this relation is a classical relation of the kinetic energy that we generally use for the classical laws and classical objects. Okay, so here this quantity v tends to c. So when you say that v tends to c, so when the v tends to c, mean this factor which comes out to be a 0, and ultimately your energy will be these things we become C. So this is 1 minus 1, they are cancel, 1 minus 1 is 0, something upon 0 is infinite, so your energy is infinite. Okay, so V is never reached to the C. Okay, so that the relations we ultimately got it over here, and these are the expressions you can remember right now. Okay, for solving any problem based on these relativistic energy laws. Okay, so these equations of total energy, kinetic energy, rest mass energy or rest energy, you say, you always write it or remember like that. Okay, so gamma factor which is always be there. Okay, so if you want to express a kinetic energy in terms of this mass, okay, so don't confuse with the particular masses over here it is using. It's not written as a m0, it should be m0 if we are designating those rest masses at the m0. Okay, so don't confuse. Okay, so small m sometimes written and sometimes it is a capital M they are written, but you have a practice to write those rest masses with the m suffix 0. Okay, so that's the mass you have, and the moving mass that is always expressed as small with not suffixing 0. Okay, so this energy relation and which we are talking about, these relations of the rest mass energy, and ultimately you are getting the expression, okay, which comes out to be a energy of the total energy we can express over there. Okay, so total energy we can express in terms of the classical I say rest mass energy by knowing this particular factor gamma we have. Okay, so here the energy is also going to be a change. That's I want to say, because the mass is going to be changed, velocity is going to be a change. So why not the energy? So energy, that the relativistic energy relation, that you have to use it by this way. Okay, you have some questions? I can take it here. Please.
तर
हा बोला बोला बोला.
क्वेश्चन असा नाहीये, पण थोडा एक डाऊट होता की ह्याच्यात प्रूव्ह करताना आपण क्लासिकल लॉज वापरलेत, म्हणजे मास आणि हे काढण्यासाठी, रिलेटिव्हिस्टिक मास आणि रिलेटिव्हिस्टिक एनर्जी वापरण्यासाठी, की कॉन्झर्वेशन ऑफ मोमेंटम आणि फोर्सचा मोमेंटमचा. तर तिकडे काही प्रॉब्लेम नाही येणार, म्हणजे क्लासिकल लॉज रिलेटिव्हिटीला अप्लाय करताना.
नाही नाही, म्हणजे तुला म्हणायचं की रिलेटिव्हिस्टिक मास काढताना आपण लॉ ऑफ कॉन्झर्वेशन हे बघ, बेसिकली laws is there, म्हणजे postulate of special theory of relativity that we are always taken into consideration. The first postulate talks about the constant speed of the light, which is not going to be a change even though the particle move with the velocity of light. Okay, that is always be a C. And the laws of motion, whatever be the motions laws, okay, they are not going to be a change. Okay, they also, so ते सगळ्या गोष्टी आपण करूनच आपण हे रिलेशन डिराईव्ह केलं. Okay,